The first thing we need to be aware of is what exponential graphs look like. So here I've got a graph that shows y is equal to 2 to the power of x against y is equal to 5 to the power of x. As you can see, they're both a similar shape, but the 5 to the power of x graph is steeper than the 2 to the power of x graph. On the graph on the right-hand side, we have y is equal to 3 to the power of minus x, and y is equal to a half to the power of x, which is actually the same as 2 to the power of minus x. Similar shape for those ones, but they go down the page rather than up. Something that all of the graphs share in common is their y-intercept. No matter what exponential graph you're looking at, the y-intercept is always going to be the same, and that's going to be 0, 1. The reason for that is anything to the power of 0 is always 1. So a to the power of 0 is always 1, doesn't matter what a is. Similarly, all of the graphs have an asymptote here. The x-axis is an asymptote. None of the graphs will ever cross the x-axis. I'm just going to add another graph in here. This is going to be y equals e to the power of x, where e is Euler's number. E is a special number that's roughly equal to 2.71828. It has special properties. So if you have y is equal to e to the power of x, the main defining property of Euler's number is that if you differentiate it, it stays the same. So if y is equal to e to the power of x, dy dx is also equal to e to the power of x. In a more general format then, if you've got y equals e to the power of kx, when you differentiate it, using the chain rule, you get k e to the kx. And that's a really important property that we need to be aware of. Now, e is roughly 2.718, so that's why I've positioned it in between the two graphs of 2 to the power of x and 5 to the power of x, because 2.718 is in between 2 and 5. The next idea we need to be aware of is that exponentials and logarithms are actually just inverses of each other. So if we've got a to the power of x is equal to b, then another way of saying this is that the log base a of b is equal to x. This is basically the definition of a logarithm. So as an example, if we know that 2 to the power of 3 is equal to 8, we can also say that log base 2 of 8 is equal to 3. Now, because exponentials and logarithms are inverses of each other, that means we can sketch the graph of log pretty easily if we remember that inverse functions are reflections of each other in the line y equals x. So if we have the graph of 2 to the power of x here, going through 0, 1, as discussed, then if we want the graph of log base 2 of x, that's going to be a reflection. Because it's a reflection in the line y equals x, means this point of intersection is 1, 0. Similarly, if we draw e to the power of x, then the inverse of e to the power of x is going to look like this. That's 0, 1. This is 1, 0. And log base e of x actually has a special name. We call it ln, or ln, however you want to pronounce it. So log base e is exactly the same as ln, or ln. Because e is a special number, it gets its own special notation for its logarithm. Another one to be aware of is log base 10. If you've got a log base 10, you can just write that as log on its own. Something else to be aware of is that log base a of a is always equal to 1, and that's because anything to the power of 1 is just equal to itself. Similarly, log base anything of 1 is always 0, because anything to the power of 0 is 1. Next, let's talk about the 3 logarithm laws. So there are 3 laws that we need to be aware of, basically rules for working with logarithms. First one looks like this. So log base a of x plus log base a of y can be written as log base a of x times y. You can write that law in terms of ln as well. So ln x plus ln y is the same as ln xy. Second law says that if you've got log base a of x minus log base a of y, that's the same as log base a of x over y, or x divided by y. The ln or ln equivalent is here. And then third and final law, log base a of x to the power of k is equal to k log base a of x. So for this one, you're taking the power of x and you're bringing it down to the front. And then the ln equivalent would be ln x to the power of k equals k ln x. Really important that you memorize these as soon as possible. So let's take a look at some examples. Example 1. Solve the equation 2 log base 2 of x minus log base 2 of 5 equals 1. First thing I'm noticing here is that we can bring that 2 up to become the power of x because of that third log law. So this is the same as log base 2 of x squared minus log base 2 of 5 equals 1. Second log law about the subtraction means we can write this as log base 2 of x squared over 5 equals 1. And then we want to get rid of that log base 2. So to do that, you're actually going to raise both sides of the equation to become a power of 2. That feels weird the first time you do it, but 2 to the power of log 2 would actually cancel out because they are inverse functions of each other. And therefore you're left with just x squared over 5 on this side, and then 2 to the power of 1 on that side. Means x squared over 5 is equal to 2, x squared equals 10. Now normally to find x at this point, we would just square root and naturally say it's the plus or minus square root of 10. Actually, with logarithms, you have to be careful. X is only going to be positive root 10, not the negative root 10. And this is because if we draw a sketch of log base 2, remember it looks like this. The logarithm function actually does not exist for negative x values or negative inputs. So we're not allowed to have negative inputs inside a log. Really important, that comes up all the time. In fact, the y-axis is an asymptote for the log function. Example 2. Solve the equation giving your answers in exact form. 2e to the power of y plus 15e to the power of minus y equals 11. Questions like this, you need to do something really specific. So what we're going to do is we're actually going to multiply every term in this equation by e to the power of y. That might seem random at first, but I'll show you why now. It's because when we do this, it means we get 2e to the power of y squared, and then just 15 on its own, because these two terms will cancel each other out. If you think about your power laws, then e to the power of minus y times e to the power of y is just e to the power of 0, which is 1, equals 11e to the power of y. If we rearrange this equation, we get this, and hopefully this now looks familiar to you. This is actually a hidden quadratic. So just to recap, for questions like this, you want to manipulate the algebra so that you end up with a hidden quadratic. Once we can see that it is in fact a hidden quadratic, we can make a substitution to make it easier to work with. So we could say something like let x be equal to e to the power of y. If we do that, then we can rewrite it as 2x squared minus 11x plus 15 equals 0. You can then solve this however you normally solve your quadratics, and you will get two answers for x. X equals 3 or x equals 5 over 2. That's useful because now we can say that means e to the power of y equals 3 or e to the power of y equals 5 over 2. And finally, we can just get y by lunning both sides. So y would be equal to ln 3 or y would be equal to ln 5 over 2. Both of those are valid because neither 3 or 5 over 2 are negative. Example 3. The decay of a radioactive substance is modelled using the formula n equals 1000 e to the power of minus kt, where n is the number of atoms after t years and k is a positive constant. Part A. Write down the number of atoms when the substance started to decay. So this is an exponential model, and if we just start by writing out the model again, n equals 1000 e to the power of minus kt. Part A, they want the number of atoms when the substance started to decay. In other words, when t is equal to 0. So all we need to do is sub t equal to 0 into the exponential model and see what comes out. E to the power of minus k times 0 is just 1. So n equals 1000 atoms. Then it says, given it takes 14.4 years for half of the substance to decay, find the value of k to 3 significant figures. So we can say that when t equals 14.4, n is going to be half of what it started at, so n would be 500. We can then sub these values into the exponential model. So we can say 500 equals 1000 e to the power of minus 14.4k. If you divide both sides by 1000, you get this. And then to cancel out the e, we're going to ln both sides of the equation. So ln 1/2 equals ln e to the power of minus 14.4k. And once again, because logs and exponentials are inverses of each other, that means ln and e cancel each other out. So you're left with just minus 14.4k on that side and ln of 1/2 on this side. You can then rearrange for k by dividing through by minus 14.4, and that's 0.048135, roughly 0.0481 to 3 significant figures. Part C, they want the number of atoms left when t equals 30. Now we can rewrite the exponential model as this, because we just found out what k was, and all that's left to do is to sub in t equals 30. That's just a case of typing into your calculator, and you'll get this. So roughly 236 atoms. Rounding to the nearest whole number there, because it's a number of atoms that they're after. Last example. The graph represents the growth of a population of bacteria, P, over T hours. The graph has a gradient of 0.6 and meets the vertical axis at 0,2 as shown. A scientist suggests that this growth can be modeled by the equation P equals A, B to the power of T, where A and B are constants to be found. Part A, write down an equation for the line. So for questions like this, I usually start by copying out the exponential model. So P equals A, B to the power of T. And then on the graph, we've actually got log P on the y-axis. So that's a little hint that you want to log both sides of this. When you do this, you can expand the right-hand side of the equation using the log laws, and you get this. And then, using that third log law, you can bring that power of t down to the front. Now, if we compare what we've got on the graph with that equation, we can see that we've got log P here and here, and this is usually where the y-axis is labelled. We've also got t here and t here, where usually the x-axis is labelled. This is showing us then that we could consider this to be y equals something plus x times something. And in fact, this is in the format of a straight line equation, because if we put c here and m here, this is just y equals mx plus c, but in a different format. So once again, log p represents y, p represents x, and then log b is our gradient, and log a is our y-intercept c. So this is why you can see a straight line graph when you plot t against log p. Now, earlier in the question, we were actually told that the gradient was 0.6 and the y-intercept was 0,2. So that means we can write the equation as log p equals 0.6t plus 2, with the gradient as 0.6 and the y-intercept as 2. Part B says, using your answer to part A or otherwise, find the values of A and B, giving them to 3 significant figures where necessary. So because we know that log A is our y-intercept 2, we can just solve this for A by doing 10 to the power of both sides. So A is 100. Similarly, we also found out that log B was actually 0.6, or the gradient. So we can find B by doing 10 to the power of 0.6, and that's 3.98 to 3 significant figures. Part C wants us to interpret the meaning of the constant A in the model. So I'd usually just write out the model again. So P equals A, B to the power of T. I'd fill in what I know. So I now know that A is 100 and B is roughly 3.98. And then having a look at this, we can see that when T is 0, P would in fact be equal to 100, or A, because anything to the power of 0 is 1. This means that A is the initial population of bacteria. And that's it. That's it for now. If you found this video useful, please do remember to like, comment, and subscribe to my channel if you haven't already. And do share this with anyone else who you think might find it helpful. Thanks, and see you next time.